Today we're going to look at a couple of topics, one called impulse, and then we're going to look at elastic collisions. Last time we saw that force can be defined as the rate of change of the momentum of an object, and if we multiply that dt to the other side, we get this expression here, which would suggest taking an integral of both sides. And if we do that and we take the integral from some initial to final state, we're just going to get the final momentum minus the initial momentum for this side. And then if we integrate over here, we've got the integral of the force with respect to time from some initial to some final time. And so this guy here is just our change in momentum. Delta P is just this thing here. And this we can redefine as a quantity called the impulse. And the symbol for impulse is J. Again, I'm not really sure why, but this really isn't anything new from what we saw last time. I mean, all of this is pretty straightforward from this expression here, but we're just giving this quantity a new name. The change in momentum we are going to call the impulse, and we're pointing out that we can take the derivative of momentum or the integral of force to relate these quantities. So oops, too far. If we know the force as a function of time, and this is typically for things like collisions where you get a real sharp peak, and the only force you have to worry about in a collision typically is the force between the two objects colliding, because it's going to be really large, and for a short duration it's going to drown out all the other forces that might be acting on the objects. So that's why we call it an impulsive force, I guess. So if we have the force as a function of time, we can take the integral of that, and this area here is going to represent our change in momentum. If we don't know the force as a function of time, we could also find the impulse by doing the average force times the time. Will also give us the impulse as shown. Alright, moving on to collisions. We have a couple of definitions for the types of collisions. So two objects approaching each other, they collide. If they bounce back, so you'll notice the magnitudes of these velocities are equal before and after the collision. If that happens, then we call that an elastic collision. Sometimes you'll hear it called a perfectly elastic collision, but typically when we say elastic, we mean perfectly elastic. Okay, here if they bounce back not quite as fast as they were going initially, or anything less than exactly as fast as they were going initially, then we call that an inelastic collision. Even if they don't stick together completely, as long as they're going a bit slower after the collision than before, we call that an inelastic collision. If they do stick together completely, sometimes that's referred to as perfectly elastic. So they just smash together perfectly. Sorry, inelastic. I have a hard time keeping the two separate. So just make sure you know what I'm talking about, even if I'm using the wrong words. Okay, the key with the elastic collisions, though, is that kinetic energy is also conserved. If you remember in the last video, we mentioned that kinetic energy is not always conserved, even though energy is, and momentum is. But in certain cases, kinetic energy is conserved. Not always, but in certain special cases that we call elastic collisions. So let's look at some of the equations we can deal with for elastic collisions. We can have an equation for conservation of momentum, so m1 v1 plus m2 v2. Ugly writing. m1 v1 prime plus m2 v2 prime. So this is just our conservation of momentum equation. In addition to that, we can have a conservation of elastic energy equation. Of kinetic energy. Having a hard time. Okay, m1 v1 squared plus 1/2 m2 v2 squared equals 1/2. And we're going to derive another equation from these two that's going to be nice and useful, and it's going to save you a lot of algebra. But if you forget it, you can always start with these two equations. It's fairly simple to remember, conservation of momentum, conservation of kinetic energy. But if you like to save yourself some work, we can simplify things a bit. So first thing we can do is get rid of all the factors of 1/2 for obvious reasons. Then I'm going to collect all the m1 terms on one side, so this term, and then factor out the m1. So that's going to leave me with m1 outside of v1 squared, that's right, minus v1 prime squared. And then on the other side, I'm going to do the same thing with m2. So we're going to get v2 prime squared minus v2 squared. You'll notice you got the prime in front here and the not primed in front there. From here we can expand this out, and so we'll end up with m1 v1 minus v1 prime times v1 plus v1 prime. There we go. Probably going to run out of space over here, but I'll cram it in there. v2 prime minus v2 times v2 prime plus v2. Hey, we made it. Alright, next step we're going to do is we're going to divide this whole thing by this equation here. Actually, back up. First of all, we're going to do what we did with our kinetic energy equation. Okay, grab my pen back. Alright, so collect the m1 terms on one side. v1 minus v1 prime equals m2 times v2 prime minus v2. Alright, now I'm going to divide by that. Sorry about that. So m1 v1 minus v1 prime equals m2 v2 prime minus v2, and hopefully you see where we're going here. We can cancel out the m's, and we can cancel out all of this stuff, and we just end up with one nice little expression here, equals v2 plus v2 prime. Switch the order there, but there you have it. Here is our two equations that we can use for elastic collisions. This one is good for all collisions because it's conservation of momentum. Do not use this one for inelastic collisions. It will give you wrong answers. Elastic only. And if we look a little closer at this, this is probably the form that's most easy to remember because it's pretty straightforward. You're just adding v1, v1 prime, v2, v2 prime. But if we rearrange this a bit, we can get v1 minus v2 equals negative v1 prime minus v2 prime. And this is kind of an interesting conceptual way of looking at this equation, because this is the difference in the speed, or the relative speed between the two objects before the collision, and it equals the relative speed of the objects after the collision, but with a negative sign. So what this means is whenever two objects collide, the speed at which they approach each other will equal the speed at which they depart, regardless of the mass, right? Mass is canceled out. That doesn't matter. You don't have to have equal masses for this equation to work. So that's kind of a cool little conceptual thing to understand. Alright, let's do a couple of examples. First of all, let's have a couple of 1 kilogram balls that are approaching each other. So same mass in this case. And before the collision, this one is moving to the right at 3 meters per second. This one is moving to the left at 2, so we've got to make sure to have a negative there. And then we want to find the speeds after they collide. So the two final velocities. The equations we start with are conservation of momentum, so m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. And then we have our conservation of kinetic energy equation, which boiled down to v1 plus v1 prime equals v2 plus v2 prime. And then we can go ahead and plug in the information we're given. So we know the initial velocities here, so I'm going to have 3 plus v1 prime equals negative 2 plus v2 prime. Here, since all the masses are equal, we can go ahead and cancel out the masses because there's the same mass in each term. So we end up with v1 plus v2 equals v1 prime plus v2 prime, which is not exactly the same as that equation up there, right? Compare those two. They're different equations, but they both need to be satisfied in this situation here. So we can go ahead and plug in 3 minus 2 equals v1 prime plus v2 prime. So when we do these types of problems, we typically end up with two equations and two unknowns, so use your favorite method for solving a system of equations. Let's go ahead and solve for v1 prime over here, and then we'll substitute it in over there. So v1 prime, the 3 is going to go to the other side, so we're going to end up with minus 5 plus v2 prime, and then if I plug that in over here, 3 minus 2 is 1 equals minus 5 plus v2 prime. Now that was just substituting in for v1, so we also have our v2 prime left here. Move that over there, and I'm going to get 6 equals 2 v2 prime, prime not squared. v2 prime is equal to 3 meters per second. Once I have that, I can plug that in here, so I plug a 3 in there, minus 5, and I can get v1 prime is equal to negative 2, and you might have guessed this from the earlier discussion. I said that the incoming speed equals the outgoing speed. Whenever you have equal mass objects colliding, that's going to mean that the velocities just swap. So this is my v2 for this was object 1 and this was object 2, right? So they just swapped speeds, and that's always going to be the case for equal mass objects. Let's do one more example. Another kilogram ball, but now I've got a 2 kilogram ball. So they're not going to swap speeds if the masses aren't equal. And let's go ahead and have them heading in the same direction this time. So this guy moving at 3 meters per second, this guy moving a little slower at 2 meters per second. So object 1 is going to catch up with object 2, and they will collide. And once again, we want to find v1 prime and v2 prime. Okay, so we've got our same two equations, v1 plus v1 prime equals v2 plus v2 prime. m1 v1 plus m2 v2 equals, you're going to get tired of writing this one probably already tired of watching me write it, but sorry, have to do it. Okay, so we plug in what we know here. We've got a 3 plus v1 prime and a 2 plus v2 prime, and we'll stop there for now. We can't cancel out the masses because we have different masses, so we're going to go ahead and plug in the masses that we know. So we're going to have 1 times 3 here plus 2 times 2 equals 1 times v1 prime plus 2 times v2 prime. And we can go ahead and solve this guy for v1 again and then substitute in over there. So v1 equals 2 minus 3, so that's going to be a minus 1 plus v2 prime. And then if we substitute that in over here, so let's simplify things a bit. This is going to be a 3 and a 4, so we're going to have 7. 1 times v1 is going to be a negative 1 plus v2 prime plus 2 more v2 primes. Move that guy over, we get 8 equals 3 v2 primes, and so v2 is 8/3 meters per second, which is approximately equal to 2.67. So we've got that guy, and then plug that in over here to solve for v1 prime. Negative 1 plus 8/3, and that is going to work out to be 1.67 meters per second. So as you expect, this one, when it collides, is going to slow down a bit. This one is going to speed up a bit. They don't swap speeds. You could check that the difference in their speeds is still 1, just like it was before the collision. So that idea still holds regardless of whether the masses are equal or not. All right, have fun with elastic collisions. See you next time.